This is Physics, Chapter 8, Section 2. I'm going to break this up into two sections. So this is going to be Part 1. Um, but Section 8, or Chapter 8, Section 2 talks about torque and changes in angular velocity. So we want to figure out exactly what this stuff torque is. We're going to be talking about moments of inertia and how that's related to rotational motion, and how torque and moment of inertia and Newton's second law of rotational motion are all related. Again, keep in mind magnitude. When we talk about magnitude, we're just talking about size. Vector has is magnitude and direction. So we're going to be looking at, this time around, lever arm and torque. And then in the second part, I'm going to talk about moments of inertia and Newton's second law. So let's get started talking about force and angular velocity. You could see, if we're pushing on a door, that how far we push from the hinge is going to make a difference. If you're pushing real near the hinge, you're really not going to have much effect on the door. If you're about halfway out on the door, you'll have some effect on getting the door to open or close, basically changing its angular velocity. If you want to have the maximum effect, you're going to push all the way out or pull on the doorknob. That's going to give you the maximum effect. The other thing is that you want to make sure that you're pushing in a direction that's essentially tangent to the line of rotation there. If you pull straight out on the door, you're not going to get much motion. If you pull at an angle to the door, it will move, but not as nearly as efficient as if you pull at a 90-degree angle to the rotation. So again, to swing the door open, you exert a force. We just talked about the various different places where you could push on this door. Obviously, the doorknob, which is near the outer edge of the door, if you exert force there at a right angle, that's going to be the most efficient way of opening or closing that door. So let's take a top-down look at our door. Here's our door jamb. Here's the hinge, which is basically where we have our axis of rotation. That's what the door rotates around, is that hinge. We're going to talk about the lever arm. The lever arm is where you're applying that force. This is basically the other side of the door. Again, when we talk about it being the most effective force, if you think of this arc here, as long as you're pushing tangent to that arc, or 90 degrees to the door, you're going to get the most efficient opening and closing of the door. So we're going to call that thing a lever arm. For a given application of force, the change in angular velocity then depends on what exactly your lever arm is. We're going to say that that lever arm is the perpendicular distance from the axis of rotation, from the hinge, to the point where the force is being exerted. Again, perpendicular distance to where the force is being exerted. For the door, it's basically it's the distance from the hinges. So we're going to let that the radius then, since that radius is important, we're going to say that the force is perpendicular to the radius of rotation. The lever arm then is the distance from the axis, basically r, radius. So what happens if you don't apply the force perpendicular, if you play it at some other angle? What essentially you do is you actually decrease the effective lever arm. Okay? So the arm is going to be reduced. If you're not at a perpendicular, if you're either pulling at an angle in or pulling an angle out away from the door and not right at right angles to the door, essentially you're decreasing the lever arm. And we could actually calculate that by this little right angle triangle. If it's 60 degrees off of the lever arm, then the effective length of the lever arm becomes the radius, whatever the original radius is, times the sine of that angle, theta. So, once again, lever arm, which we're going to call L, can be calculated. L is going to be radius times sine theta, where theta is the angle between the force and the angle of rotation. So torque. What is torque? Torque is a measure of how effective a force is at causing rotation. So for instance, this is a wrench, and it's tightening up a nut on a bolt, and so the torque is how much force you're applying to that nut. Uh, there are in the industry there's places they give you the values for torque. They want to know how, depending on the size of the nut you're torquing down, you have to make sure you apply the correct amount of force, rotational force. We call that torque. The magnitude of torque then is produced by the force on the lever arm, because the force is measured in newtons. In America, we measure torque in foot-pounds, foot being the weight, pounds, or foot being the distance, and pounds being the weight. Since we're doing this stuff in SI units, newtons is our weight, and meters is our distance. So instead of foot-pounds, we have newton meters. We just reverse the two measurements. We're going to use the Greek letter tau, a lowercase tau, and that then becomes the lever arm, which is the radius times the sine of theta, times the force, whatever the force is. So then we will get, so the force is going to be measured in newtons, and the lever arm is going to be measured in meters, and so we get newton meters. So for instance, if you're trying to tighten up a bolt on an engine, the torque value might be 35 Newton meters. It says if you're using a 25 centimeter long wrench and you're pulling on the wrench, but you could only get the force at an angle of 60 degrees, maybe it's a weird angle on the wrench. It says and asks how long is the lever arm and how much force are you going to have to apply. It's going to probably be something different than the torque value. So how do we go about finding this out? Well, let's take a look at our sketch. We have our 60 degrees. We have our 25 centimeters. We're going to calculate the lever arm. The lever arm, again, is going to be shorter than 25 centimeters. It's going to be reduced by the sine of theta. So whatever the sine of 60 degrees is, we're going to reduce the lever arm by that amount. We know what the torque we're trying to achieve is. Now we got to figure out how much force we have to apply to get that 35 newtons. We don't know what the lever arm really is. We know what the length of the wrench is, but again, the lever arm is shortened because our angle is different. And then we're going to try to figure out force. Okay, so how do we go about solving this then? First of all, let's figure out what the lever arm is, r sine theta. So r is 0.25 meters, 25 centimeters. Theta is 60 degrees, so we do the calculation, and we come up with 0.22 meters. So we reduce it by about 3 centimeters. We're going to plug that in. R sine theta, or L, we're going to plug that in. We know what the torque we're trying to achieve is over here, and now we're going to calculate F. If we rearrange this first, we divide both sides by r sine theta. So we're going to take our 35 divided by the 0.22 that we calculated earlier, and we get 1.6 times 10 to the second newtons, or 160 newtons. So if we're at this cockamamie angle and we don't have a meter long torque wrench, we have to apply 160 newtons to get 35 newton meters of force on the bolt. Correction units, force in newtons. Okay, that's all looks good. We solve for the unknown. We did all that. Let's take a look at another one.
Get 2 pencils, some coins, and some transparent tape. Tape 2 identical coins to the ends of the pencil and balance it on the second pencil, as shown here. Each coin exerts a torque that is equal to its weight times the distance from the balance point to the center of the coin. The torques are equal and opposite in direction. Thus, the net torque is 0. You could add a second coin on top of one of the two coins, thereby making the two forces different. This makes the net torque greater than 0. Hence, the pencil rotates in the direction of the net torque. You could also slide the balance point toward one end or the other of the pencil, thereby making the two distances different. The pencil again rotates, but this time due to the difference in R1 and R2.
Okay, that's it.